Okay, let's have a look at maps. Maps in eCognition. So what are maps in eCognition? Maps is a concept of having more or less a sub-project within your project. So within one project you can have several maps. Actually, if you've been using eCognition, you already used a map, which is always called the main map. And but additionally, you can create different maps or additional maps to the main map that you already have. And yeah, maps are independent sub-projects. That's how I always envisioned it for me at the beginning. It will make sense if you use maps in your projects, but at the beginning it makes sense to think of maps as sub-projects within your main project. And as stated before, the original scene is always the main map, so you always have at least one map in the project, and that's going to be the main map. And all the other maps that you create, you can give them different names, individual names as you like. And the maps also can have the different resolution, different vector layers, different extent, so they are totally more or less free from the other maps, right? And that allows you to use it in a very interesting way. And I'm going to show you some use cases how you could use it. An important question would be how to create maps. So if you're interested in maps, how do you create them? There are different ways. First of all, you can create a map right away while creating a project. Or also if you're using customized import, there's also a tab where you can define multiple maps for the project. So that can be done. I'm going to show you how to create additional maps in the rule set itself. That's very flexible. That's how I use maps actually. And the algorithm for that is copy map. So copy map can be used to create additional maps in a project in the rule set. And if you're using the source view window, there's also a tab at the bottom where you can create additional maps. So different ways. I'm going to show you the rule set way because that is transferable and it's implemented in your workflow. Now, after you know how to create maps, probably would make sense to ask yourself the question, how can you use it or why should you do it? Are there some applications of maps? Yes. So you could use a map, for example, to back up the original image object. So if you do a segmentation and then in the rule set you're altering the objects, but you want to keep the original state somehow in the project, you actually can create a copy map after the first initial segmentation and store more or less the initial segmentation results on that second map. So actually you can try out new segmentations or classifications, and then you can compare those changes to the copied map and also recover the original state by synchronizing the content of the backup back to the main map again. You also could use maps to do or apply independent segmentations and also classifications for different tasks. So on the main map you could do a segmentation, very fine segmentation to detect small features like single trees, for example. And on the copy map you could do a large scale segmentation and detect water bodies. And actually you can fuse that data or the information of those two maps again back together to the main map and have one wall-to-wall classification, or at least combine those segmentation and classification results from those different maps in your project. And that actually means that you can create totally independent and different image object hierarchies within one project using maps. And again, you also can have totally different layers in a different map, right? So you can have only layers that are interesting for water segmentation in the copy map, map 2 or whatever. And on the main map you have other layers that are more interesting for vegetation classification and segmentation, right? And you can fuse the results back together, so they are not lost somehow. You always can get them back into one map. You also can use maps to improve performance. If you're using, for example, downsampling approaches, as stated before, you can actually reduce the spatial resolution of a map. And you also can rotate maps actually, and you also can create small subset maps, so only representing a small area of your whole scene. And yes, using, for example, the downsampling for the copy map and then doing a segmentation there and classification of large-scale objects. Again, I'm using the example of water surfaces. That's going to be way faster if you have less pixels in the map. And then you can transfer it back to the main map where you have the high resolution and then maybe do a refinement on the outline. But yeah, that's going to improve the performance. And yeah, you also could use regions to improve performance, and regions can be used to create small subsets within your scene, so within your project. And then you can create a copy map only using a small subset, so a small region, apply the segmentation or the analysis only on the small subset, and then transfer that information back to the main map. And that's also going to improve the performance. Now a few points on why using maps makes sense. So again, that's a bit of repetition, but you can process on individual maps only. So the image object domains of maps act independently from one another. That's very important to understand. And what you do in one map does not impact another map. So you can do a totally different segmentation or refinement on a different map, and the main map, for example, is not affected. But the content can be exchanged between the maps using the algorithm Synchronize Maps. And we're going to use this as well in the example that we're going to have a look later. And also the transfer layer algorithm is there to transfer raster layers from one map to another. And you also can delete maps. So if you're not needing if you don't need a map anymore, you can simply delete it and keep the project small. Okay. Okay, in the exercise that I'm going to show you now, we are actually looking at the second bullet point that I showed you, this different segmentations in different maps, and we're also going to have different data sets in different maps. So what we want to do is a change detection using maps. And we're gonna have two time steps, time step 1, time step 2. We're gonna have actually 3 maps, the main map where we have all the data, then we're gonna create a copy map of only the time step 1 layers, and another map T2 of only the layers for the second time step. And we're gonna create a segmentation and classification on each map, only using the respective layers of that time step. And afterwards, we're gonna fuse the data back together on the main map and detect change. So that's the goal. We want to see how did it change between these two time steps. And actually, I think the scene is from the Amazon area somewhere. And we have Sentinel-2 data, 2 time steps, and I reduce it to blue, green, and red, so only 3 bands. But that's going to do the trick for us. And again, we're going to do a classification of time step 1, a classification of time step 2, and those going to be separate in separate maps within eCognition, and then we're going to fuse the results on the main map and going to have a change detection result. So what will you learn? You will learn how to create independent maps, and we're going to create one representing only time step 1 and the other time step 2. So we're going to reduce the layers for each map. And we're gonna classify vegetation on both maps individually. So we're gonna have 2 classifications, and then we're gonna synchronize the content of both those T1 and T2 maps back to the main map. And then we're gonna somehow classify the change between those 2 classifications. Right? And for the change detection, we're gonna do it again on the main map. So we're gonna first actually synchronize map T1 to the main map. So we have the results of the T1 map, the classification on the main map. Then we need to copy the image object level on the main map and synchronize in the third step the results of the T2 classification onto the second level on the main map. So we're gonna have 2 levels then on the main map after we have synchronized both maps to the main map. And then as a next step and final step to actually detect areas that have changed, we're gonna introduce a third level on the main map. We're gonna call it level change. And then we're gonna use the relationship or the connection between the different levels in our image object level hierarchy to detect change, right? So we're gonna implement a process that checks if there has been vegetation in T1, so our level T1, and also on T2. If this is the case, then there is no change. If we have vegetation on T1, but not on T2, we have a negative change, right? Vegetation has been removed. And also the other way around, if you don't have vegetation in T1, but on T2, we have a positive change. So we have vegetation growth. And that also nicely shows how you can use image object level hierarchies in eCognition to, in this example, to classify change between two time steps. Okay, enough talking. Let's have a look at the data. And first of all, we're gonna create a project. So we're gonna load the data that you're gonna find in the data folder. And you're gonna see two TIFF files, the same tile, but two different dates, one acquired in 2016 and one in 2021. So I'm first gonna drag and drop 2016, and we have 4 bands. So actually this is Sentinel-2 reduced to 4 bands and also reduced to 40 meter spatial resolution instead of having a 10 meter spatial resolution. So first thing I'm gonna do after loading the data, I'm gonna rename the aliases so I know what I'm looking at. And let me check. It is, oh no, it's RGB. It looks good. Okay, so this is red T1. T1 stands for time step 1. Green T1. This is blue T1. And then we do have a near infrared. And layer 5, 6, 7, 8. This is the second file. And actually, if you cannot remember and you want to have the connection between those aliases and the files in the Explorer, you also can use the view, source view. And that gives you exactly that information. So you see now red T1 is the first band of this file here. And that can be very helpful, especially if you're loading a lot of data. And yeah, this is the T2 2021 and layer 5 is the first band of that one. So you also can rename it here. This is going to be red T2. Red, green T2. Blue T2. And here, T2. Okay, looks good. It also updates in the view setting. That is awesome. I'm quickly gonna split the view and display the first time step on the top pane and the second time step at the bottom. And side by side view. So things have changed. You see this spot here in time step 1 has changed, this area. And now is agriculture, I guess. So what we want to do is compare those two time steps using maps, right? We haven't touched maps yet, but we're gonna do in a second. What you need to know is that this drop down here, which says main, it's only filled with main. That's the main map actually that you have by default if you load data. So you always have one map in eCognition, and that's the main map. And you also cannot rename the main map, but we're gonna create a copy map T1 and another map called map T2. And in those maps, we only gonna have the respective layers, and we're gonna run a rule set in the different maps separately. Then we're gonna have a classification of vegetation, non-vegetation in those maps for T1 and T2. We're gonna synchronize those results to the main map that you see here. And then we're gonna do the change detection and compare those two classification results. So that's what we wanna do. And that's what I wanna show you. So let's jump in and develop a rule set. First, I'm gonna create some structural processes, add new process, and I'm going to use insert child process. You also can use Control A and Control I, and that's what I actually like to use. first is going to be the first structural process, going to be change detection using maps. And if you then use Control I, it's going to insert a child right away. And the first thing we're going to do is create maps. And I'm simply gonna insert a few more. I insert a child, so it doesn't matter. Okay, so let's put that here and here and here and here. All right, first thing is we're gonna create maps, and in this case I discussed that previously, that you have different options how to create maps, but we are gonna go for the one that is creating maps using the rule set. And I'm gonna insert a child here into the create maps, and I'm gonna look for copy map. And for the copy map, you do have a lot of algorithm parameters. Yeah, we're not gonna touch them. Some of them we're gonna touch. First of all, what you have the target map name, and we're gonna rename that to map T1. So we first want to create a copy map only having the layers with T1 of timestep 1. Use variable as scale, no. Scale relative to main map, no. So you can scale it, right? You can rotate the map, you can resample the map, and what we are looking for is image layers. So you can define which image layers you want to have copied, and I'm only looking for the T1 layers, right? 4 of those, and I want to have those copied to the map T1. And if you have thematic layers, you can also choose if you want to copy the thematic layers. If you have an image object hierarchy and samples and so on, you also can define if you want to have copied, for example, the image object hierarchy, or if you want to have a clean map, so to say, without image object. So that's up to you. Yeah, I'm gonna hit OK, and I'm simply gonna copy and paste this copy map to map T1, and I'm gonna rename the target map name to T2, and I'm gonna change the image layers to the T2s, and then I'm gonna execute the parent process. I'm gonna click OK. I'm gonna execute the create maps, and that should create actually now 2 maps, and you see it's very fast. And now we have 3 maps actually in the project. The main map, map T1 and map T2. I'm gonna unsplit, perfect. And now in the drop down menu here, you see we have the main map, map T1 and map T2. And the definition here in the drop down defines what you see in the view. So if I go to map T1, you see the number of layers is reduced, and those are the layers actually that we have copied to this map T1, only the T1 layers. And if we now go to map T2, we only have T2 layers. You also can use split view, display map T1 at the top and map T2 at the bottom, side by side view, and now you have it. So we're looking at maps now, different maps, and not only at the main map. Okay, now the next step is that we want to classify vegetation, non-vegetation in the different maps. So first what we're going to do, we're going to create a rule set that classifies vegetation, non-vegetation in this map, the map T1, and then we simply can copy and paste that section and change in the domain settings the map T1 to map T2, and then it's going to be applied the same section onto the map T2. And what we want to do is first we're going to create a temporary layer called custom brightness. Then we're going to do a segmentation. We have pixel-based object resizing in there, assign class, and then merge region and remove objects. Let's start developing that rule set. I'm gonna go fairly fast here. Classify on map 1. Okay, I'm gonna insert a child process here, and first we're gonna use layer arithmetics, and we're gonna create a customized brightness layer. And the output value in this field, you define the formula, and actually I'm gonna do it like this: red T1 plus green T1 plus blue T1 divided by 3. Okay, and the output will contrast. Thanks. I'm setting the output layer type to a 32-bit float. So we are on the safe side here. And do not execute yet. Okay. I'm first gonna click OK. And before I click OK, let's have a look here at the domain. So you see you have the option here of map. So you could change the map here to map T1. That means it only is processing this process on map T1. Or map T2, right? So it will create a temporary layer in map T2. On map T2, it wouldn't work because you have defined here T1 and T2. So it's not really transferable in this case. So we have to adjust that in a later stage for the map T2. But by default here in the domain, you have from parent. And what that means is it looks at the parent process. What the heck is the parent process? I'm gonna hit OK here, and as you remember, I've chosen here insert child process. That means it's a child of this parent process, and in the domain of the child process we defined that the map definition should be taken from parent process. Okay, now we can have a look at the parent process, which is here, and here it also says from parent. That's the default settings. But you can change it here, for example, to map T1. And that means that all the consecutive child processes, or all the child processes of this parent process, gonna look into the definition, into the domain definition of the parent process map T1, as long as you leave the default settings here in the domain settings for the map. If you leave that as from parent, it's gonna check the parent definition. And I'm gonna execute it to show you that. And you see we are looking at the map T1 up here. That's the map T2. Map T2, we don't have an additional layer, but map T1, we do have the custom brightness. And that's just the brightness layer that I want to use to discriminate vegetation, non-vegetation. That was a simple approach. It's not very sophisticated. But yeah, it helps to, in this case, discriminate vegetation, non-vegetation. So that's what I'm gonna use. And now in the next step, we're gonna segment the image and classify right away using the multi-threshold segmentation algorithm. So multi-threshold segmentation. Again, the map from parent, so it's gonna look at the parent process definition. That's gonna be fine. We wanna call the level T1. That's gonna be the resulting image object level. Image layer is going to be the input, the customized brightness that we've computed for this T1 map. And minimum object size is going to be 100, so it doesn't create pixel-sized image objects. And then we're going to create two classes, and the threshold is going to be 900. So I played around a bit, and 900 was giving me good results. And everything below 900 is going to be classified as vegetation T1. And everything above that value will be non-vegetation T1. Okay, again, execute it, and it only will apply on the map T1 because that's the parent definition of the map in the domain of the parent process. Alright, so again, map T1 at the top, map T2 at the bottom. We don't have a segmentation on map T2. They are totally independent. And we do have objects and classified objects on map T1 because we did the multi-threshold segmentation. That looks good. I'm gonna implement two pixel-based object resizing algorithms, and I'm gonna adjust the settings so we're gonna smooth the outline of our objects a bit, and we're gonna get rid of these zigzag outlines. It's just gonna be a bit smoother and more appealing. So let's simply use pixel-based object resizing. And first, what we want to do is grow. So we want to grow. We actually want to grow vegetation, grow. Oh, I called the level T exclamation mark. Ah, interesting. So I'm going to rename it here, and then it's going to be renamed in the whole project. Okay. Level T1, Okay, let's come back to the pixel-based object resizing. So we want to grow vegetation T1, so improve the outlines, and also if we grow or shrink vegetation T1, the non-vegetation objects will be influenced. That makes sense, especially when we grow. So we're gonna grow into X and Y direction, so we're not gonna change that. Class filter doesn't matter. We don't want to have layer constraint. The interesting thing down here is the candidate surface tension. Set this to class. So it's gonna look at the class vegetation T1, and we class filter right vegetation T1, and if this is greater equal to 0.5, then grow. And we're gonna do this 5 times. So number of cycles set to 5, and that's gonna be the settings. And what this actually will do is, let me see, so we're gonna grow. Yeah, so it's gonna grow from green into this orange area, and it's gonna remove actually more or less those in-reaching object features from the non-vegetation. Yeah, I think that's a good area. So let's execute this one and see how the result looks like. Yeah, we have smoothened the outline, and in the next step, that's always what I do, a back and forth between growing and shrinking. So we now grew, and now I want to shrink, and shrinking means I want to close those small features off that are now vegetation reaching into the non-vegetation area. So I'm simply going to copy and paste this pixel-based object resizing, change growing to shrinking. The class for new image objects, I'm going to put that into non-vegetation. I'm going to scroll down, and yeah, value, change that around, the operation, sorry, from greater equal to smaller equal to, and executing this 5 times, that should close off those things here. And I've put the new objects that were created by the shrinking directly into the class non-vegetation T1. And now I'm simply gonna go for a merge region. Again, we don't have actually to change something here, because map is important. That's looking at the parent process definition. We just have one level, and by class that's all fine, so we can leave the default settings, and that's gonna clean up our objects. And yeah, now we do have some small objects left. Those were created based on the growing and shrinking, and you can simply apply more or less a minimum mapping unit using the remove objects algorithm. What we do here is we define a condition. So what objects do you want to remove? And I'm interested in objects with a certain area. Oops. So if you go under object features, geometry, extend area in pixels in this case, you can change that to square meters or hectares or whatever makes most sense to you. I'm gonna set the value to 100. So all objects that are smaller than 100 pixels, please remove those objects. And how do I want them to be removed? You can display the advanced parameters, and you see that by default it's set to merge by shape, and you can change that to merge by color. And shape simply means it's gonna merge, if the object is smaller than 100 pixel, it's gonna be merged into the surrounding object with which it shares the longest common border with. Hope that makes sense. So let's execute this, and small objects should be removed and dissolved, right? And that's gonna be the final classification result for this T1. Simple, straightforward, and we applied quite a bit of smoothing, but yeah, that's up to you. And yeah, so we have one classification done. Now the easy part actually is to apply that also on T2. So what I'm actually gonna do is I'm gonna create a new structural process and gonna call it independently. Gonna insert this classify vegetation on map T1 into that one. And now I'm gonna copy and paste this whole parent process, classify vegetation on map T1, copy paste. Now we have the same thing here. I'm gonna rename that to T2, and in the parent process, that's very important, change the map to map T2. And we need to do one more thing, because I hard-coded here this brightness. It's not ideal, but that's what I did. I'm gonna rename those layers to T2, otherwise it wouldn't work. And cast brightness, and actually it doesn't matter that we have the same name here, because it's gonna be in a different map, so it's not gonna override the existing cast brightness for T1, okay? That's it, actually. Yeah, the naming is not perfect. Just see, I called it level T1, you simply call it level 1 or something. But that's gonna create now in our map T2 a level called level T1. I don't want to change that now, it doesn't matter actually. So I'm gonna execute this whole thing, and it's gonna run through it, and then we should have a classification on map T2 using exactly the same workflow, the same rule set as for T1. Let's have a look here. Right, I updated the view, I just zoomed in a bit, and now we have it. So exactly the same rule set applied on two different maps, two different separate classifications that we now want to fuse and synchronize on the main map. So that's map T1, that's map T2, and remember we still have the main map, and the main map is, as you see on the left hand side, if we look at the main map, it's empty. We have the input layers, the importer layers, but we don't have an image object level and nothing. So now what we want to do is fuse and synchronize the results of those two maps into the main map. And that's actually pretty easy. I'm going to display the main map on top left and also here. And this is going to be map T1 and that's going to be map T2. You actually also see here in the window at the bottom right which map is displayed in this view, right? So main, map T1, map T2. Yeah, let's go ahead and try to synchronize the results to the main map. We're gonna use an algorithm called Synchronize Map. But first I'm gonna create a structured process. And I'm gonna insert a child, I'm gonna look for this Synchronize Map. And I'm going to define the target map name. The target map is going to be our main map. And we want to create a level here, level. Now we have to make sure it's T1 and T2. Level T1, no class filter, nothing, no rotation. And yeah, in the domain, you have to define the map. So we copy from map to T1, the level T1, and we want to synchronize this to our main map and also call it level T1. That's already it. Let's execute this one. And you see here in the main map, we now do have a level T1, and that's representing 100% our objects on the map T1. Actually, also nice to see because there's a certain transparency. Whoops, here. And we display here the T2s in the background, the input images, and we have overlaid it here with our classification results from T1. So you see there's a difference, and that's exactly what we want to detect. In the next step, we want to synchronize the results of the T2 map. And what we have to do is, in order to get those results to our main map, we need to use a copy image object level of our level T2. So we're going to copy it one level above, and then we can synchronize our map T2 results to the main map. Otherwise, it would override our existing level. So we need to have a level. So if we already have a level and we want to synchronize the map, we need a target image object level to synchronize with. Otherwise, we will override it. So I'm simply going to use a copy image object level on the main map. So from parent, that actually is in our case the main map. And we're gonna call it level T2 and copy level above. That is important. And then we should have two levels and they are identical. And now I'm gonna use the synchronize map. I'm simply gonna copy and paste it. I'm gonna synchronize the map T2 and the level is also called level T1. It might be a bit confusing, but you know why I did it. It was just a mistake by myself. Yeah, and now it's important that we want to synchronize those results to the main level, but to the level T2 in the main level. And very important now for the second synchronized map is that you change the synchronized complete hierarchy to no. Otherwise it will overwrite also the information of the level T1 on the main map, and we do not want to have that. So execute this one, and it's going to take a bit more time to execute because it is synchronizing already to an existing image object level and an image object level hierarchy, right? So it's a bit more complex than simply copying image objects to pixel level or to pixel domain where you don't have image objects, and then it simply takes a bit longer if you're synchronizing already existing hierarchies. I think that makes sense. And we do have a result now, and because we do have the opacity turned on, you actually see both results displayed at the same time. So I'm gonna unsplit the view and only look at the main map. And now we have the level T2 classification and so the map T2 actually classification, and that's the level T1. And if we overlay those two, you see those areas that are now here displayed in this darker orange. That's now a combination more or less of, or it's a combination of the green color of the level T1. And on level T2, it's the orange color, so no vegetation, and that means those areas have changed. And now we want to classify those areas on the main map. We have both maps, both results in our main map. We also can delete the maps that we don't need anymore here. Map T1, there's an algorithm, delete map, and you can simply remove those if you're not needing them anymore. But we are gonna go straight into the change detection. That's gonna be interesting. 04 change detection, and that's gonna be the last step that I want to show you here. First thing I want to do is I want to have identical objects, image object outlines on both levels, and we currently do have larger image object outlines on level T2 because that's the super level, and we have smaller ones. It's actually a combination of the map T2 and T1 objects on level T1, and that's simply based on the image object level hierarchy dependencies. So one sub object only has one super object, so one sub object cannot have multiple super objects, and the other way around, the outline of a super object or a super level, those outlines are always gonna be found on sub levels. They're always gonna be there, so you couldn't actually merge objects on level T1 that are separate objects on level T2, right? So you would need to merge them on level T2. Okay, but that's image object level hierarchy dependencies. But because we want to have the same image object outlines on T2, I'm gonna use a algorithm called convert to sub objects, and that's simply gonna cut all image objects that are found on a sub level into the super level. And we can leave the default settings, simply hit execute, and then it's simply gonna add those outlines and objects to the T2 level. And again, if you remember my introduction slides or the theory part, we actually have both classifications now on the main map in two different levels. Now we want to create a third level where we classify change. Okay, so we're gonna simply do a copy image object level and we're gonna call it level change. And that's gonna be, of course, above the T2 level. Execute this, we should have 3 levels, and the level change is gonna be the level that we're gonna classify the change on. And if you remember that graph that I showed you, what we're now gonna check is vegetation, so we're gonna, based from our level change, that's gonna be our super level, our analysis level now for the change, we're gonna look 1 level below if there's vegetation and also compare it to the classification on 2 levels below. And if those classifications are both vegetation, we don't have a change, right? So we label it as no change. If we find vegetation on level T1, so 2 levels below, and no vegetation on 1 level below, so on T2, we're gonna label that as change because there has been vegetation removed, right? And also the other way around, if on level T1 we do not have vegetation, but on level T2 we do have vegetation, we also have a change, but a positive change, positive meaning vegetation increase. And yeah, so we need actually to create those classes. We need to define the class definition. And before we do that, I'm gonna clean up or remove the classification on our level change because we wanna relabel it. And there's also an algorithm which is called remove classification. And there you simply have to define the level change, execute it, and then it's gonna remove the classification. Here, it is still on the other levels, right? So we still have the classification on the other levels. So we didn't remove our results. Okay, now what we are going to do is actually create the classes here. And in the class hierarchy, I'm gonna create a class called change and a class no change. And we're gonna have 2 different no change classes. We will have vegetation, no change, and we're gonna have no vegetation, no. Okay, the naming is a bit off, but you get the idea. And I'm gonna put those into the class no change. So no change is gonna be the parent class, and you simply can drag and drop it onto the no change. And then it's gonna be a child class. And for change, we're gonna have also 2 classes. Vegetation increase, that's gonna be bright green. Vegetation decrease. Okay, I'm gonna change the color of this change to an orange color. Okay, something like this. And vegetation increase gonna be a subclass of change, and also the vegetation decrease. And now how do we connect those levels and the information of the sublevel and so on? What we will do is define what you see in the graph into a class definition in our class itself. So what we are going to use is an algorithm to classify those classes called classification. And that algorithm actually looks at a class definition in the class hierarchy. So we need to define the class definitions here in our 4 classes. But before we get into the change detection, I quickly want to clean up my project and rename the classes actually so it doesn't get too confusing for you and also for me. So what I did is I called the classes Non-Vegetation T1 and Vegetation T1 and used them also for the map T2. So I think that is confusing, and that's why I'm gonna go in here and simply gonna rename the Non-Vegetation. I'm simply remove the time label because this is irrelevant. And so this should be Non-Vegetation. And I think that's already it. Let me check. Yep, so this should be all good. So if we're going now into map T1, you see that we have the classes non-vegetation and vegetation, and it's not labeled with the time step T1 because the labeling is already done in the map, so we know what we are looking at, and that's also non-vegetation, vegetation. And if we're going back to the main map, that's also there. So we have two different levels. And I just changed the naming of the class, and now we're gonna start with the change detection, and I hope it won't be too complicated for you. Actually, renaming the class makes it a bit easier, and what we now need to do is we need to define the class description in the class itself. Let's start with vegetation no change here. So if you double click the class in the class hierarchy, and then double click this and min, you can insert expressions for that class. And we are simply looking for a threshold expression, add new and condition. We are now interested in the information of sublevels, right? Because we want to classify the level change here into our new classes based on the information of those two sublevels, level T1 and level T2. And yes, for this class, which is called vegetation no change, that is the case if we have vegetation on both sublevels, on level T1 and level T2, right? So both time steps. And where do I get this information? If you go to object features, relations to objects, sub-objects, and there you get a list of features that you can use, and we are looking for the existence of. And actually we need to create this one. So double click that one, and we are interested in this case for vegetation. Okay, so create existence of vegetation distance 1, that means 1 level below. And we're gonna create 2 of those, one with distance 1 and one with distance 2. And this 1 means it looks at the sub-objects of 1 level below and checks if it's vegetation. If it's vegetation, this feature returns a 1. If not, it returns a 0. And yeah, if this is true, and adding another condition, the same is true for 2 levels below. Also for vegetation. Okay, if this is also true, so if both conditions are fulfilled, vegetation on 1 level below and vegetation on 2 levels below, which represent our time steps, then you are vegetation no change. I think that makes sense. Now the same for non-vegetation no change, so that's the other way around. So we have to look for the feature that is checking the class non-vegetation. So the same here, object features, relations to object, sub-objects, existence of, and actually we can choose here, if you right click, create for all classes. Let's see. You might save some time. Yeah, non-vegetation 1, that means it checks 1 level below for non-vegetation, and the value here is 1. So if it's non-vegetated on 1 level below, and also sub-objects existence of. Let me check. Yes. So actually, so what I did is first I clicked here, create new existence of, create for all classes, and that created by default for all classes this distance of 1. But I already had a vegetation 2, so looking for vegetation 2 levels below. And if you right click on that one and say create for all classes, it's taking the parameters that you have defined here in this feature creation for vegetation 2. In this case, the only thing that you can change is the 2, and then it's going to create the distance. And then if you choose right-click, create for all classes, it's going to create it for all classes using that specific parameter for the selected feature here. So that was nice. So I simply can click the non-vegetation 2 if this is true. So if both conditions are true, then you are non-vegetation, no change, because it has been non-vegetation for both time steps. Now we need to do a cross-check vegetation increase. What is vegetation increase? Actually, vegetation increase would be if the first time step, so 2 levels below, that is our T1, if this is non-vegetation, and if we do have vegetation on 1 level below. And also you could do the easier actually only with sub-objects, existence of sub-objects, vegetation. If you're using for value to 1 and 0, you wouldn't need to create a non-vegetation, right? Because we just have 2 classes. If you have more classes, it makes sense to do it like this. But you can actually save some time. Then vegetation decrease, that is if you have in time step 1 vegetation and in time step 2 you don't have vegetation. So a decrease, so vegetation on 2 levels below, yes, but no vegetation on 1 level below. Okay, I think that makes sense. Hit OK. Close. Okay, so we now have defined class descriptions in all our 4 classes: vegetation decrease, increase, and the 2 no change classes. And now simply what we need to do is add a new process, and we are looking for the classification. And we have to make sure that the level is level change, and we select here the active class, the class that we want to use for classification. And this algorithm then looks into the class definition in the classes, and it's going to use those for classifying our image objects. Hit execute, and we should receive a classification on our level change. That looks good. And now what you see in red is vegetation decrease, green is increase. Those are mainly patches that were within agricultural areas in time step 1, and then some vegetation is detected on time step 2. And those, yeah, the red areas are vegetation removed, so they increase the agricultural area, so they expanded a little bit. And then with actually no changes, gray area, and the bright gray or almost white is non-vegetation, no change. So that has been non-vegetation in both time steps. And the dark gray is vegetation, no change. So that has been classified as vegetation on both time steps. Yeah, and we still have the information on our other levels, so you could actually have a look at those as well. And yes, that would be the final result. You could export this now, export statistics, what area has changed. Maybe let's do this. Let's add an export to this, and then we're done. So that's 0.5. And I'm gonna insert export project statistics. And the features, I'm interested in the area. So under map features, objects, you're gonna find area of classified objects. Let's unfold this. Right click here, create for all class. So we have the area for all classes. And I am interested in vegetation decrease. And if you right click, you can change the unit. I want to have this in square kilometers. Adding this to the right side. Vegetation increase, also square kilometers. Alright, that's it. I'm gonna export those 4, hit execute, and that's gonna be exported to the workspace directory or to the input data if you haven't saved or created a workspace. Let's quickly check this. Yeah, so you see here the results folder in the directory of the data because I haven't saved the project yet. And you're gonna see project statistics and that CSV file. I'm quickly gonna open that one. And there you have your results. Area of vegetation decrease in square kilometers. And area of vegetation increase and so on. So that's the data that we have exported. Alright, so that's it. We had a look at maps and how to apply it for or use it for change detection. You also can simply use maps for backing up your segmentation results or testing different segmentation routines and workflows and comparing your results within one project. You always can synchronize it, the results. You also can send raster files that you've created in a separate map to the main map, for example, or to any other map. So that's also possible. And the algorithm here is called transfer layer, and that's gonna transfer a layer to, or multiple layers to another map. All right, just think about how you could use it, doing different segmentations, different classifications in one project, fusing them together, different time steps, backups, and so on. Maps actually increase flexibility in your workflow, in your rule set development, so try it out, see if maps help you, and if you get it up and running. Let us know what you think, and have a great day.